So this question appeared in IIT-JAM 2018 examination. The statement is, two boxes A and B contain an equal number of molecules of same gas. So we are having two boxes A and B where the number of gas molecules, they are same. So Na, that is equal to Nb, and let's say this is equal to N. Okay, and if the volumes are Ba and Bv, okay, what the volume they are given to be different, Ba and Bb, and further it's also given that corresponding mean free path of the gas molecule in respective boxes, it is lambda A and lambda V respectively. Okay, now the question is, then which one of the following these four options given, which one is going to be correct? Okay, so let's take a look at what we have learned in theory. So the mean free path of the gas molecule, as we know, it is given by lambda. This is equal to 1 divided by under root 2 n sigma. What is n here? So n is the number density, n, that is equal to n divided by b. Okay, so it's given that the number of gas molecule they are same, but the corresponding volume into which they are confined, they are different. Okay, so accordingly the number density, that's going to be changed. Okay, so and what is sigma? Sigma is equal to pi d square, where d is the diameter of the molecule. D is diameter of molecule. Okay, so with this information we can rewrite this as B divided by under root 2 n pi d square, because the gas molecules which are confined in two different boxes, they are identical. So from here we notice that the mean free path, it's simply proportional to the volume of the box. Okay, so therefore we can write for two different boxes lambda A upon Ba, this will be equal to lambda B upon Bv. So therefore option D is correct one here. Which one of the following figures correctly represents the TS diagram of the Carnot engine? Okay, so let's try to understand it. So we know that a Carnot cycle, it consists of four different reversible processes. Okay, so here it's a PV diagram for the Carnot cycle. Okay, here process A to B, this is an isothermal process which takes place at temperature T1, and during this step a given amount of heat is transferred to the working substance at temperature T1. Process B to C, here process B to C, this one. Okay, process B to C, it is adiabatic, reversible adiabatic. In fact all these processes, they are reversible in nature. Okay, so this is reversible adiabatic process. Okay, and then because when this process B to C it's taking place, it's an adiabatic process, so that means it's an expansion, so there is no energy exchange between the system and the surrounding here. Okay, so because the gas it's expanding, so it's expanding at the cost of its internal energy, so temperature will fall from T1 to T2. So here ultimately this C to D process, this is isothermal compression here, and then again from D to A, it's an reversible adiabatic compression. So this is adiabatic compression, this one, this is reversible adiabatic compression. Okay, now we want to understand it in terms of the temperature entropy diagram. So let's see how we can translate this PV diagram into the temperature entropy diagram. So let's take T temperature along the y-axis and entropy along the x-axis. Okay, so we will start from the process A to B. So as I said earlier, process A to B is it is reversible isothermal process. It is reversible isothermal process, and it takes place at temperature T1, fixed temperature. So that means here, if I want to draw this process A to B on a TS diagram, so it will be like this. Okay, so starting point it's A and end point it's B. Okay, and it's taking place at constant temperature. Now the process B to C, it's again reversible adiabatic expansion. So we know that in a reversible adiabatic process, the entropy change that is delta S, that is equal to 0. So here, so that means this process will take place at fixed entropy. So delta S is equal to 0. This implies that S final, that is equal to S initial. There is no entropy change here. So I can draw a straight line which is perpendicular to the entropy axis here. Okay, so here this is point C. So now we are at point C here. Okay, now C to D, it's again a reversible compression. Okay, the reversible isothermal compression, and this process now, because the during the adiabatic expansion, okay, the temperature of the gas, it has fell to a new value which is T2 here. Okay, now C to D, because it's an isothermal process, again this will be parallel to the entropy axis. Okay, so this is C to D. Okay, and this process will be at temperature T2. Now D to A, it's an again adiabatic compression. So during this adiabatic compression step, the temperature of the gas, it will increase again to initial value of temperature T1. Okay, so if we compare the given options, the option B here, that is the correct one. The equation of state for 1 mole of a non-ideal gas is given by PV is equal to, so we are given the equation of state for 1 mole of a gas, PV, that is equal to A into 1 plus B by B, where it's given that A and B, they are temperature dependent quantities. Okay, if the volume changes from V1 to V2, so we are given that volume, it changes from V1 to V2 in an isothermal process, the work done by the gas is given Y. Okay, so we have to identify the correct option. So here we will make use of the general expression for the work that we use for evaluating the work done in any kind of thermodynamic process. Okay, so but before that, we are going to rearrange the given equation, the equation of state, because we need the pressure for the calculation of the work done. So pressure, after rearranging this equation, we can rewrite this as P, that is equal to A upon B plus B upon B square. Let's call this as equation 1. Okay, so the general definition of the work in any kind of thermodynamic process, that is W, that is equal to P dV, and then within appropriate limits of integration, because here we are given the volume, it's changing from B1 to B2. Okay, so now we will make substitution of P here by making use of equation 1. So this can be rewritten as A by B dV from B1 to B2 plus B1 to B2 B by B square dV, and this after integration, it will yield, this will gives us, so A by B dV, that will give you ln V. So ln A outside because it's a temperature dependent quantity. It has nothing to do with the volume. Okay, so that's why we can keep it outside. A ln the final volume B2 upon B1, okay, and plus B by B square. So B is because B is constant. Yes, so not constant, it's temperature dependent, so we can keep it outside the integral. And then 1 by V square dV, that will give us minus 1 by V. Okay, minus 1 by V, and then from V1 to V2, then upper limit minus lower limit, that will introduce another negative sign. So ultimately we can rewrite this as, sorry, I made a mistake here. So this is going to be equal to AB. Okay, so here also AB, and here also we will have AB, and then minus 1 by B, and then volume changing from B1 to B2, and that will finally result in 1 upon B1 minus 1 upon B2. So this is our final answer, and let's see with which option it matches. It matches with option C. Okay, so A ln B2 by B1 plus AB into 1 by B1 minus 1 by B2. So therefore C is the correct option here. An ideal gas consists of three-dimensional polyatomic molecule. Okay, so it's a three-dimensional polyatomic molecule. Please pay attention to the statement. It's a 3D polyatomic gas molecule. Okay. Okay. The temperature is such that only one vibrational mode is excited. So it's also given that it's a sufficiently large temperature such that one vibrational mode is excited. Okay, if R denotes the gas constant, then the specific heat at constant volume of 1 mole of gas. So we have to evaluate the specific heat at constant volume. So that is, we have to evaluate what is CV for 1 mole of such kind of gas molecule. Okay, so this we can do by simply evaluating that how many degrees of freedom one single gas molecule is having. Okay, so because it's a three-dimensional polyatomic gas molecule, so translational degrees of freedom are T, that is equal to 3. Okay, and then what about the rotational degrees of freedom? Okay, because it's a three-dimensional gas molecule, so if we are having, for instance, we are having a linear let's say diatomic gas molecule, then it will have only two rotational degrees of freedom. The third rotational degrees of freedom, it cannot be excited in a linear gas molecule. Okay, so here because it's three-dimensional gas molecule, so instead of 2 we will have 3 rotational degrees of freedom here. And now it's also given that one of the vibrational mode is excited. Okay, so then we have to look for that how many vibrational degrees of freedom will be there, because if we just take a look at the, for instance, this the diatomic gas molecule, and if we consider the vibrational degrees of freedom here, so vibration is always accompanied with the kinetic energy term and then a potential energy term. Okay, so this kinetic energy terms, when we take the average of the energy, so this will contribute to 1 by 2 kT of energy, the kV, that's the Boltzmann constant, and this potential energy term, it will also contribute to the average energy of half kVt. Okay, so when it's because it's given that one vibrational mode is excited, so that means here we have to consider two energy terms here. Okay, so therefore total degrees of freedom are 3 plus 3 plus 2, so we are having total degrees of freedom, they are 8. So therefore the average energy per gas molecule, that is equal to 8 into 1 by 2 kBt. Okay, so that is equal to 4 kVt per gas molecule. But now we have to calculate this value for 1 mole of a gas, such kind of gas molecule. So let's say that is U, so that will be simply Avogadro number multiplied by average energy per gas molecule, that is equal to 4 Na kBt. Now this the product of Avogadro number and Boltzmann constant, that will gives us the universal gas constant, that is equal to 4 RT. Okay, so now Cv, that's the heat capacity at constant volume per mole, that is equal to du by dt at constant volume, and that is equal to 4r. So therefore our correct option here is C. Consider an ensemble of thermodynamic system, each of which is characterized by same number of particles. Okay, so we are having an ensemble of system where number of particles is same, and pressure it's also same, and temperature is also same. So we are having these three variables which are same for the given ensemble. The thermodynamic function that describes such an ensemble is, so we have to look for the correct option among the given four options. Okay, so here I'm going to take an example of the Gibbs free energy, and then let's try to understand whether our choice it matches with the given constraint or not. Okay, so as we have learned in thermodynamics, the Gibbs free energy, this is equal to H minus Ts. Okay, so here H is the enthalpy and T is the temperature and S is the entropy. So from here I can write for a small change in the Gibbs free energy, dG, that is equal to dH minus TdS minus S dt. Okay, and here I need the value of dH, so that can be calculated by knowing the thermodynamic potential, which is enthalpy H is equal to U plus PV, and that comes out to be dH, that is equal to du plus pdv plus vdp. Okay, so by substituting this value of dH here, we can substitute du, that is equal to TdS minus pdv. So we have replaced du with this expression. It's basically from first law of thermodynamics. Okay, plus remaining two terms, plus pdv plus vdp. Okay, so pdv and pdv, they will cancel with each other, so finally dH will be TdS plus vdp. Okay, so here we are going to replace dH, that is equal to TdS plus vdp minus TdS minus S dt. So some of the terms will cancel this one. Okay, so at the end dG, we are having dG, this is equal to V dP minus S dt. Okay, now when dP is equal to 0, okay, let's call this as this is equation 1 and this is equation 2. Now in equation 2, when dP is equal to 0, let's say dP this is equal to 0, so this implies P, it's a constant. Okay, and when dt is equal to 0, okay, this implies T, that's also some constant. Okay, so that means when both of these quantities, that's pressure and temperature, they are constant, so this implies that dG, that is equal to 0, so that means G is a constant. Okay, so therefore for the given conditions, so G, in fact it's also related to number of particles in a system, and that's further related to the chemical potential. So okay, so mu, that is equal to Gibbs free energy per particle, or you can say that G, that is equal to N mu. So this also doesn't change for the as mentioned in the statement of the question. So therefore all these three conditions, they are satisfied by Gibbs free energy. Okay, and in case, so let me just extend the discussion here. So although it's not asked, but it's really important to learn. So in case we are having a mean option, for instance, we can say that the number of particles, temperature and volume, okay, if they are constant, okay, then the correct option would be option B here. Okay, so for instance, I can write the same way as we wrote expression for dG, we can write the expression for the small change in Helmholtz free energy, and that will turn out to be minus S dt minus pdv. So when dt, that's equal to 0, that will gives us T, that is constant, and when dv, this is equal to 0, this will imply that V is equal to constant. Okay, and both of these, when these are constant, so dF will be 0, this implies F is going to be a constant quantity. Okay, so therefore, so in this case the right option would have been option B here. which of the following relations is true for the thermodynamic variable? So we have to look for the correct relations one by one. So here we will continue with the first option, that's option A. Let's try to check whether it's correct or not. Okay, so the option A. Okay, so here I'm going to continue with the entropy. So we can assume entropy to be a function of temperature and volume. So we can choose any two thermodynamic variables. Okay, so here with this information we can write a small change in entropy ds, that is equal to ds by dt by keeping the third variable constant, and then dt plus ds by dB by keeping the third variable constant. Now it's temperature, and then multiply by dV. Okay, now multiply both sides with t. Okay, so that is t ds, that is equal to t ds by dt at constant volume dt plus t ds by dV at constant temperature dB. Okay, now this the first term here on the right hand side, TdS by dt at constant volume. So TdS, that will give you dQ, so that is, it is basically dQ by dt at constant volume. So this is nothing but heat capacity at constant volume, that is TdS, that is equal to CV dt plus T ds by dB. Okay, so here we will make use of the Maxwell, one of the Maxwell relation. Okay, what is that? So ds by d, I can write by making use of the Maxwell relation, ds by dV at constant temperature, this is equal to dP by dt at constant volume. Okay, so after replacing we obtain plus T dP by dt at constant volume, and then dB. Okay, so that means, so let's take a look at whether what is the equation that is given in A, option A. Okay, so this is TdS, that is equal to CV dt. Okay, that's what we are having, plus T dP by dt at constant volume multiplied by dV. Okay, so that means option A is correct. Okay, now let's check whether B is correct or not. Okay, so for this we will consider another function, because here we are having Cp dt. Okay, so now we, instead of considering entropy to be a function of T and V, we are going to consider entropy to be a function of T and P. Okay, so we are changing one of the variable, and by following a similar procedure I can write ds, that is equal to ds by dt at constant pressure and multiply by dt plus ds by dP at constant temperature. Now again multiply by T on both sides, so then we will obtain T ds, that is equal to T ds by dt at constant pressure dt plus T ds by dP at constant temperature dP. Okay, so this is the first term on the right hand side, it TdS by dt at constant pressure, that will give us Cp basically. Okay, so TdS, that is equal to Cp dt. Okay, now again we will make use of the Maxwell relation. So here ds by dP, so let's see, this is equal to what? ds by dP at constant temperature. Okay, so this is equal to Sp, then we will have a T in the denominator here and B in the numerator. Okay, and then constraint of constant pressure. But now make note that because P and T, they are not on the same side of the this partial derivative, so here we will have a negative sign. Okay, so when P and T, as was the case in previous option A, P and T, they are coming on the same side of the partial derivative, so therefore we were not having a negative sign here in between these two while equating these two partial derivatives here. So when P and T, they are on the different opposite sides of the partial derivative, so then we will have a negative sign in that particular Maxwell relation. Okay, so we are going to replace this ds by dp at constant temperature with minus dv by dt at constant pressure. So I can rewrite this as minus t and dv by dt at constant pressure and then multiply by dp. Okay, so let's see whether it's the same thing that that's given in B. Yes, TDS, that is equal to Cp dt minus T dv by dt P dp. Okay, so that means option B is also correct here. Okay, now let's check the option C. Okay, in C we are given dF, that's a Helmholtz free energy. Okay, so Helmholtz free energy, because it's given by F is equal to U minus Ts. So from here dF will be du minus tds minus s dt. Okay, so du, that is tds minus pdv. Okay, so I am replacing du with this expression minus tds minus s dt. Okay, so from here tds and tds, they will cancel out and ultimately we are left with, that is equal to minus pdv. Sorry, it's sdt, not sdv, it's sdt, sorry, minus pdv minus s dt. Okay, is it correct? No, it's given in a wrong way. It's minus s dt plus pdv. Okay, there should be a negative sign, not a positive sign here, so therefore this is incorrect. Okay, now what about the option D? Let's see, it is dg. Okay, so g is equal to h minus ts, and as we did in the previous question, in the same way, a small change in g, that is equal to dh minus tds minus s dt. So here we have to substitute the value of dh here, and when we do that, ultimately we will be left with dh, that is equal to tds plus bdp. Okay, so that means no, sorry, that is dh. Okay, and then minus tds minus s dt. Okay, so this will cancel with this quantity and ultimately we are left with vdp minus sdt, vdp minus sdt. Yes, so that means D is also correct. So here three options A, B and D are correct. A, B and D are correct here. So we are given a monatomic ideal gas which is operating in a closed cycle as shown in the PV diagram here. Okay, the ratio of P1 by P2 is, so we have to find the ratio between P1 and P2. So it's given that the PV diagram of the gas, it's given. Okay, so let's try to figure out the corresponding parameter. So because it's given that the process between this point and this point, it's adiabatic. Okay, so the pressure at this point, let me mark this point as A, okay, and this point as B. Okay, so at point B, the pressure is P1 and the corresponding volume is, it is 3V1. Okay, and at point A, the pressure is P2 and the corresponding volume is B1. Okay, now because it's an adiabatic process, so that means it is bound to satisfy PV power gamma, that is equal to constant. Okay, so let's write this equation for these 2 points A and B, because A and B, they represents the equilibrium states. Okay, so at point A I can write P2 P1 power gamma, that is equal to P1, the value of the pressure at point B, P1, and then value of volume which is 3v1 and its power gamma. So this equality should be satisfied. So we have to find the value of P1 by P2. So from here we can easily write P1 by P2. This is equal to V1 upon 3V1 and its power gamma. Okay, and that's nothing but 1 by 3 power gamma, because it's given it's a monatomic ideal gas. Okay, so for monatomic ideal gas we know that Cv, this is 3 by 2 R per mole, and Cp, that is equal to 5 by 2 R, so that gamma turns out to be equal to 5 by 3. So if you substitute the value of gamma here, so this will be equal to 1 by 3 and its power 5 by 3, and then after calculating it you will find that its value is equal to 0.16. so that's going to be our answer. Okay, so 0.16 is our answer. So let's continue with the next question. The statement is, consider the first order phase transition of sublimation of zinc. Assume that the vapor to be an ideal gas and the molar volume of solid to be negligible. Experimentally it's found that so we are given an equation which is satisfied this system during phase transition. So log P, that is equal to minus C1 by T plus C2, where P is the vapor pressure in Pascal, T is in Kelvin, and C1, the value of constant C1 and C2 they are given to us. The latent heat of sublimation of zinc from the Clausius-Clapeyron equation is. So we have to make use of the Clausius-Clapeyron equation for this system, and then let's try to see how we can solve this problem. So the Clausius-Clapeyron equation for the given situation is given by, it is dP by dt, that is equal to L by T, and then the molar volume. Well, it's a sublimation, so so that means it's a solid to gas direct transition, Vg minus Vs. So that's the actual form of the Clausius-Clapeyron equation. So note that here Vg and Vs, these are the molar volume. Okay, in gaseous form, and Vs it's also the molar volume in solid form. Okay, so that means it's a volume divided by the number of mole basically. Okay, so because we are given a situation where the molar volume of the gaseous phase, that is Vg, it is much larger than Vs. So this is given in the statement of the problem. So we can approximate this equation to be equal to L divided by T into molar volume of the gaseous phase. So we are also given that the gaseous phase satisfies the ideal gas equation. So that means we can write for the gaseous phase P Vg, where Vg it's the actual volume of the gaseous phase, and that is equal to nRT. So that means this can be rewritten as P Vg upon N, where this becomes the molar volume, and this is equal to RT. Or we can write this as P Vg. Now this small Vg is the molar volume, that is equal to RT. Or from here we note that the molar volume Vg, that is equal to RT by P. Okay, so now we will make substitution of this Vg here in this equation, and then see how this Clausius-Clapeyron equation look like. Okay, so dP by dt, that is equal to L by T, and then the value of Vg, which is RT by P. So P will come in the it is P upon RT. So this is equal to PL upon RT square. So this equation can be rewritten as, let's call this as equation 1 and this as equation 2, so that equation 2 can be rearranged as dP by P, that is equal to L by R dt by T square. Okay, so now after integration we obtain ln P, that is equal to minus L upon RT plus some constant of integration C. Okay, let's call this as equation 3. Now this equation can be further rewritten as 2.303. So basically we are changing this from ln into logarithmic to the base 10 form. So a factor of 2.303 will come into a picture. So 2.303 log 10 P, that is equal to minus L upon RT plus C. So this is equation 4. Now this can be further rewritten. Actually we want to write this equation in the form of equation which is given to us, so we have to adjust the coefficient, the constant term here with the other terms. So this can be rewritten as log to the base 10 P, that is equal to minus L upon 2.303 R into 1 by T plus this constant as it is, and then divided by this constant term which is 2.303. Now we have to compare this equation 5 with the given equation, this one. Okay, so after comparing these two equations, what we obtain is that L is equal to 2.303 R multiplied by C1. The value of C1 is given to us in the statement. So this is equal to 2.303, and then substitute the value of the gas constant which is 8.314, and then multiply by the value of the C1 which is given 6790. And after the multiplication, the value that we obtained from this, that is 130.0 kilojoule per mole. So that is our answer. Okay, so here we should have 130.0. So that completes the question.